Hello and good morning to everyone. So our today's lead code question is 153, which is find minimum in rotated sorted array. So in this question we are given that suppose we are given an array of length n which is sorted in ascending order and it can be rotated between 1 to n times. So what does that mean? Suppose this is our nums array 0 1 2 4 5 6. So if it is rotated one time, then this 7 will come at the first and it will become 7 0 1 2 4 5 6. So it is after one rotation. So here we can see this 4 5 6 7 0 1 2 is the same array after rotating four times. So see here it is given that rotating an array one time results that the last element will come at the first and the whole array still will be the same. And then so in this question we are given a sorted rotated array nums having all the elements as unique, and what we have to do is we have to return the minimum element in the array, like we return the smallest element of the array. And also we are given that we have to write an algorithm which runs in of log n time, right? Of log n time. So let's see the examples. So if you see, our sorted array would be 1 2 3 4 5, but it is rotated three times. So these three elements, that is 3 4 5, comes in the first part, and we get this rotated sorted array. And now what you have to do is we have to return the smallest element. So 1 is the smallest element, so that could be our answer. Sorry, that is our answer. But how we reach to that answer, that will be looking in the video in the approach part, right? So let's see the constraints. So here n, which is our nums dot length, and n can be up to 5000, right? That is 5 into 10 k power 3. And nums of I is from minus 5000 to 5000, right? So each element in the array can be from minus 5000 to 5000. And it is also given that all the integers of nums are unique, means there are no duplicate elements present in the nums array. And nums is sorted and rotated between 1 to n times, right? So let's move to the approach part. So initially our array is sorted in increasing order, but after rotation the array becomes somewhat like this, right? After four rotations the array will look like this. But if we see in this array, the left part, that is 4 5 6 7, is still sorted. Even the right part 0 1 2 0 1 2 is also sorted. So the sorting breaks at the point where the minimum element lies, right? If you notice this left part 4 5 6 7, 4 5 6 7 is still sorted. Then the right part 0 1 2 is also sorted, but the overall sorting breaks at the point where the where the minimum element of the array is lying, right? Is lying. So so the array is almost, and we are given that the array is almost sorted, and we have to think of some solution of log n time. So we can use binary search. So we'll be using binary search over here. So let's see. So we have taken this example 6 7 6 7 1 2 3 4 5, right? So if you see, what is the middle element of this array? Middle element is 2. Middle element is 2, and the right element is 5. Right element is 5. So if we see our middle element is lesser than right element. Middle element is lesser than mid element is lesser than right element, right? So what does that mean? That means the array from mid to right, if we see the array from midpoint to right point is sorted properly, right? Is sorted properly. What does that mean? That means our what we call smaller element or our smallest element is either present at the mid, is either present at the mid or or before mid, right? Even we can see in the example, this part is properly sorted, but our smallest element is present before mid. So when r so when nums of mid is lesser than nums of mid is lesser than nums of right, then the right half is sorted properly. This condition means our right half is sorted properly, and our minimum element may be present either at the midpoint or on the left side. So now what we do is, now instead of searching in the whole array, we'll search in the left half, that is from 0 to mid, right? So this is the first condition to reduce our search space. So if we get this condition, that is the middle element is smaller than the right element, then what we make, then we reduce our search space and make right is equal to mid, right? So this is the first condition. Then let's see what let's see this example. So here we are 4 5 6 7 0 1 2. Now our mid element is 7 and right element is 2. Now in this case our mid is greater than right. Mid element is greater than right element. That means see, we have discussed that our left side and right side, they are separate, they are sorted separately. So if our mid element is greater, that means our right side is sorted and right side is increasing order, and this is our mid element, right? So if mid element is greater, that means our minimum element cannot be present on the left side. Minimum element cannot be present on the left side, right? So it will be somewhere between the mid plus 1 to right, right? So our minimum element will be somewhere between the mid plus 1 to the right. So what do? We search in the right half. So we update our left is equal to mid plus 1, right? So these are the two cases or conditions. So first one is mid element is lesser than right. That means our element will be on the left side. So what we'll do is we'll update our right as mid, our right equal to mid. This is the first case. Or the second case is mid is greater than right. Mid is greater than right. That means our element cannot be on left side, so we'll search on the right side and we update left is equal to mid plus 1. Here we are doing mid plus 1 because middle element is not the minimum element, but here middle element can be the minimum element. That's why we are doing only right is equal to mid, not mid minus 1. So these are the two conditions for the binary search. So let's try to see with the help of an example. So we have taken the same array 4 5 6 7 0 1 2. So initially we will take two pointers, left is equal to 0, right is equal to, that is the size of the array, which is 6. Then in iteration 1 we find the midpoint. So midpoint is 3, that is 7. Then we compare middle element and right element. So at middle element we have 7, at right we have 2. Now 7 is greater than 2. That means our minimum element is on right side. So we update our left to mid plus 1. Mid element is 3. Sorry, mid pointer is 3 plus 1. So now our search space is 0 1 and 2. 0 1 and 2, right? Search space is 0 1 and 2, and our left is at 4 and right is at 6. Now our left is at 4, right is at 6, and we have 0 1 and 2. Now again we find the mid element. So mid, at mid we have 1, and at right we have 2. Now mid is lesser than right. So in this case our element is on left side, so we update our right equal to mid. We update our right is equal to mid. So now our right is equal to 5 and left is equal to 4. Right is equal to 5 and left is equal to 4 again. So now our search space is 0 1. So again our mid, that is 4. Mid is 4 and 0 is less than 1. Again 0 is less than 1. So we again update our right. So our right is again equal to mid and mid is equal to 4. So now in the iteration number 4, in the last iteration our left is equal to right, which is equal to 4. So we are left with only one element. So we return that as our answer. So let's see the code part. So in the code part we take two pointers initially, left which is at 0 and right which is at the last point, that is nums.size minus 1, and then until our left is not equal to right, then we find the middle element, and then we check our two conditions. If nums of mid is lesser than nums of right, then our element will be on the left side, element will be on the left side, so we update our right pointer equal to mid. Else our element will be on the right side, so we update our left is equal to mid plus 1, and then at the end we return nums of left pointer. So that is our answer. So I hope I am able to explain you the solution properly. So if you like the video, please make sure to like, share and subscribe the channel. Thank you.